Okay, it is my pleasure to introduce Dr. Wenbin Zhang. Currently, Wenbin is a postdoc at Carnegie Mellon University. Before that, he earned his Ph.D. in information systems from University of Maryland, Baltimore County, and he has a master's in computer science from Memorial University in Newfoundland. Dr. Zhang's research is at the intersection of AI and fairness, and so we're excited today to have him here to share the research that he's been up to and to teach us about the intersection of these fields. Thank you.
Thank you, Casey, for the nice introduction. And I believe it should be still morning time in Oakland. So good morning, everyone. My name is Wenbin Zhang. I'm a postdoc at Carnegie Mellon University. It's my great pleasure to see all of you virtually and to share with some of my work that I've been working on. Some of them are closely related to Center for Health AI's mission. For example, ensuring health equity, as well as our everyday life, such as our mortgage loans, our children university application, and internet traffic. Hopefully we can have a good discussion. Oh yes, I might not able to read the chat or to see you, so feel free to jump in to ask questions. Okay, I start with a little bit background relating what I've been working on. So I work on the fundamental research with the aim of addressing computational and algorithmic issues, as well as other applications motivated by use cases. So in general, my work falls under the umbrella of machine learning, artificial intelligence, or data science. Nowadays, we talk about these terms on daily basis, which has also been recognized as an emerging field. Most basically, it has split into a wide spectrum of fields with applications such as healthcare, security, manufacturing, and finance. Among them, some applications are dynamic in nature and are also of great importance with wider applicability, ranging from telehealth, traffic network, protein unfolding. In the meanwhile, the dynamic property of the environment also brings unique and complicated challenges, such as real-time reprocessing and non-stationary data distribution. Therefore, devising new models becomes essential. Here shows the general overview of a dynamic environment, in which, as you can see, natural temporal ordering of the observation and can normally be indexed in time order. The observation for a given period could also be expressed as deriving in some way from past observation. In addition, the observation can be represented by different data structures such as linear array and list, as well as non-linear data structures, e.g. trees and graphs. So the work covered in this talk focus on both non-linear and linear data structures in dynamic environment, targeting respective crucial domains. Since my PhD study, I've been exploring such challenging dynamic environment and working towards making dynamic environment models simpler, fairer, and more efficient. So specifically, my work has spanned different areas such as social aspect of AI, deep learning, or data stream mining, with applications in different domains, including health informatics. Most of my research works are publicly available. I also contribute to related open source software, such as the MOA, Massive Online Analysis, which is the most popular open source framework for data stream mining. My fairness work, which I'm going to discuss later, it also be integrating into the IBM Research AI Fairness 36 Toolkit. Due to the time constraint, I will not able to cover all of them in details. I will focus on two things among them, learning fairness and graph generation. Specifically, I will introduce two online decision trees with fairness to support this kind of social fairness, and a generic framework of factorized deep generative model for interpretable dynamic graph generation. Then can provide necessary complement to this important yet challenging task. Here's the roadmap. I'll learn the just mentioned two topics. I'm also going to briefly discuss other project that I have been working on. Hopefully we can find more common interests and discussion. And I will conclude with future works. By the way, feel free to interrupt me if you have any questions. I also have some backup slides with more details. Okay. Now I will start with the first one, online decision tree with fairness. Part of this work was supported by my founded IP at Leibniz scholarship proposal, which also support my research visit at Germany. This work also contribute to two subsequent grants, bias and no bias, addressing bias and discrimination at various stages of the AI systems. As previously discussed, artificial intelligence are increasingly popular. So AI-based decision systems have also been widely used to automate all types of decision makings, including allocation of resources, issuing of mortgage loans, and personalized marketing. However, significant concern on the potential discrimination during AI decision-making process have been raised. As a recent example, the report from ProPublica found that Black patients were underrepresented in clinical trial, even when a treatment was aimed at a particular type of cancer like disproportionate impairment. In addition, the state-of-art clinical prediction models although underperform on them. One might think of the immediate solution could be just to ensure that AI models do not have access to the sensitive attribute. For example, the race attribute that we just discussed, unfortunately, this is not the case, as the sensitive attribute could correlate with other attributes. As an example, it was discussed that Amazon Prime showed the sign of racial discrimination by excluding Black people from service and amenities, although race is not even shown to the AI system. So in addition, AI bias is just a complex problem which could arise at all stages of AI-based decision-making process, starting from the problem selection and all the way to the post-deployment. Other than previous discussed racial discrimination, AI can be just as bad as human, or even exacerbate all types of real-world disparities, such as gender inequity and age discrimination. Such incidents have therefore sparked heated debate. So pulling scholars from diverse of areas such as public health, philosophy, and law. In fact, the policymakers across the world are also becoming increasingly aware of the issue of AI adaptation roadblocks, and they see the algorithmic accountability as an important topic. For example, the US Congress has been trying to pass the Algorithmic Accountability Act, which would mandate accountability of the algorithmic systems. This increasing attentive issue has therefore motivated a number of approaches to prevent bias and discrimination, and giving rise to a new field of research, we typically call it fairness-aware learning. However, most of them tackle fairness as a static problem, assuming the full data can be afforded for multiple scans and the underlying data distribution does not change. However, in many real applications, data is generated in an online fashion, and its characteristic might also evolve. In addition, existing fairness studies have largely focused on maximizing fairness with the minimal loss in accuracy, but an effective and robust mechanism is expected so as we can allow a flexible control on the trade-off between fairness and accuracy in order to instantiate application-wise fairness-aware learning. Therefore, AI fairness for such sort of application should be able to simultaneously address these challenges, which is the target of our approaches. Before we get into the methodology, I will first discuss the problem definition. So we here are trying to addressing fairness. However, defining fairness is also a hard problem per se, depending on many factors, context, as well as stakeholders. So there are more than 20 measures of fairness already proposed in this direction, and but there's no consensus on which one is more versatile than others. So in this work, we adopt the widely used statistical parity, like examining whether looking into whether the probability of being granted for a benefit is the same for both deprived and favored communities. However, note that our approach can accommodate other fairness notions such as equal opportunity seamlessly. Existing studies integrate static parity in static setting. Take this figure as an example, assuming gender as a sensitive attribute and a binary classification problem. So the static parity basically examines the proportional difference when being granted a benefit between male and female. When extended to the online environment, we tend as accumulated static parity to account for discrimination up to the current time t. So the aim of online fairness learning is then to maintain a fair and up-to-date classifier, which can make accurate prediction, but does not discriminate a certain community on the condition to scan multiple massive and possible even infinite sequential instance just once, while adapting to the evolving distribution, both class distribution as well as the discrimination distribution, as discrimination could also evolve. I will also briefly discuss the general idea of decision tree and the Walina-Hopton tree just in case. So as the name goes, use a tree-like model of decisions and use a pure list of the data to decide on which attribute to use for splitting, typically based on information gain. Here is an example in which the tree needs to be decided the splitting based on either attributes A1 or A2 for a binary classification problem. You see here the number along with its following positive or negative sign represent how many instances belong to that particular class. So here, A1 will be chosen as after the splitting, both its child node mostly consist of instances belonging to one class, leading to the most uncertainty reduction. So here, just to say, after splitting, we are more assured of the class label of the instance. Note that information gain and the other metrics from the information theory are from data encoding perspective, and they do not consider fairness. Now I will discuss our base model, the Walina-Hopton tree, compared with the traditional decision trees. It scans each example, arriving continuously in the sequential setting only once, and stores sufficient information in its leaves in order to grow. So the crucial decision when constructing the Hopton tree are how and when to split a node. They also imply the Hopton bound to guarantee that a splitting decision is aesthetically identical to the decision of a conventional static learner, like the one we just discussed. So such decisions are based on information gain to optimize for predictive performance and do not consider fairness. In addition, Hopton tree does not adapt to the evolving data distribution, which could have impact on both accuracy and fairness. In this work, we extend the Hopton model in two ways to enable fairness-aware learning in massive and stationary setting, as well as massive and non-stationary scenario. To this end, we first introduced two splitting criteria: the fair information gain that jointly considers the gain of an attribute split with respect to classification and also with respect to discrimination. And the second, adaptive information gain that additionally take evolving data distribution and the fine-grained control of fairness into consideration. So we then propose two respective algorithms incorporating the newly proposed splitting criteria to fulfill different online fair decision-making environments. As discussed, information gain optimize predictive performance, but does not consider fairness. To balance data encoding and diminishing discrimination, we propose to alert the splitting criteria to also consider the fairness gain of a potential split. So to this end, we first define the fairness gain when splitting on attribute A. Here, the formula is where D subscript B are the additions induced by A. So in practice, the fairness gain compares the discrimination before splitting against the discrimination after splitting and aggregates the weighted discrimination on each resulting subset. Its absolute value is used here to capture reverse discrimination, i.e. discrimination against the favored community. So the corresponding discrimination value for each additions are computed based on the previous discussed statistical parity. The idea of fairness aligns with the idea of information gain, and both of them are the higher the reduction, the merrier. The distinction is that the merit of FG is evaluated from a discrimination perspective, while IG pays attention to accuracy. We then combine fairness gain and the information gain as a joint objective. We call it a fair information gain that evaluates the suitability of a candidate splitting attribute in terms of both predictive performance and fairness. Intuitively, the fair information gain closely combines information gain and the fairness gain. The iterative tree induction process therefore takes into account the influence of the split under evaluation, both on the task distribution as well as the discrimination of the resulting tree. For attributes that their split does not change the distribution, i.e. Fg equals 0, their Fig is reduced to Ig. Note here the trade-off between accuracy and discrimination can also be achieved by combining Ig and Fg through other operations, e.g. addition. However, these two matrices are not necessary in the same scale in practice, and the value of them can be incompatible, which means one can be dominated by the other. Multiplication is therefore favored our addition. Another merit of multiplication is that it encourages fair split, which means it giving priority to splitting candidate that result in the reduction of discrimination, or those that increase discrimination. That's to say, FG becomes negative. When the data distribution is non-stationary, the incurred concept drift could also have implications on both accuracy and fairness. To adapt to such scenario, we further propose the adaptive fair information gain, which adopt to the evolving relationship between the class and the feature. Such flexibility also opens the door to adapt to applications with various performance constraints, thus enabling customizable fairness-aware learning. To this end, we first reformulated previous introduced FG and defined the universal fairness gain by crossing out the fairness gain ratio for two reasons. First, the massive data string setting, especially with non-stationarity, so certain attribute value could discontinue for a period of time. Second, the weighted representation favors global discrimination, our local discrimination. We then combine FG and UFG as a natural exponential function along with an additional tuning parameter gamma here, which allows for a flexible control on the trade-off between accuracy and fairness. Here, the meaning of adaptive is twofold. FIG can adapt to application with various performance constraints by presenting different gamma values, which can kind of enforce respective importance of fairness when we build the tree. Alternatively, FIG can also adapt to the evolving relationship between the class and the feature by adjusting the value of gamma on the fly. So here the exponential function in the function of AFIG is used for smoothing. Note that AFIG can still hold FIG's other modalities, such as promoting fair split. Now I turn into the two respective algorithms, encoding the newly proposed splitting criteria to fulfill different online decision-making requirements. So here, picturize the first fairness-aware Hopton tree induction process with instance arrive continuously. Perhaps can store sufficient information only at its leaf nodes exclusively for tree growth and generalize better after incorporating more examples into the model. From the decision tree region perspective, the decision regions are further divided for fair decision making. So when the underlying distribution is non-stationary, we further propose 2C Fahad, which basically extends the Fahad model compared with the Fahad. Other than the splitting criteria difference, 2C Fahad also maintains sufficient information at non-leaf nodes so as to create this kind of alternative decision subtrees when evolving data distribution is detected at the node. So when an alternate subtree already exists, 2C Fahad can check whether the alternate branch performs better than the old branch. The old branch will be replaced by the alternate one if so. Otherwise, the alternate branch will be prolonged. So in addition, evolving distribution may have different implications on accuracy and fairness. So to manage such implications on the fly, 2C Fahad also leverage the previous introduced tunable parameter gamma to adjust the importance of fairness according to concept drift implication on accuracy and fairness. Now I will briefly discuss part of the experimental evaluation. We evaluate our methods on the benchmark adult and the sensor dataset. Here shows the prediction accuracy and the fairness performance as typically in the domain of AI fairness. So to study the behavior of our approach, we consider baselines from respective domains. To study the domain, first, well, the pure accuracy driven Hopton tree, which is also the base model of our method. Second, the recently proposed fair online learner, FEI, which is the only online fairness work in the literature to the best of our knowledge. We also incorporate other fair splitting criteria into the Hopton tree model as additional baselines. Last, the representative concept of adapting learner hat. So the obtained results are summarized in the table here with the best performance of the compared baseline mark in boldface. The percentage in parentheses is a relative performance difference out of the best baseline method. So in this result, it's clear that our models are capable of diminishing the discrimination to a lower level while maintaining a fairly compatible accuracy. The design of our model also provides a clear mechanism to manage the trade-off between fairness and accuracy. This can be necessary when an initial model does not meet one of these requirements, so allowing the end user to make adjustments. Our model controls thus by predefining the value of gamma parameter, as gamma is in proportion to accuracy. Increasing its value leads to a higher accuracy at the expenses of a higher discrimination. Such expected trend is clear from the results visualized here. So clients can therefore accommodate their need according to their respective constraints. In our paper, we also evaluate the structural effects on the tree construction by looking at attribute selection strategies when building a tree, McNamara test, testing whether our criteria actually work to benefit the positive classification of the deprived group and the Pearson correlation of coefficients between sensitive attribute decision boundary and the actual boundary to verify our theoretical design. Okay, that's all for this work. Any question before I start the next one? Okay, now I turn into the graph generation part. This work was part of the funded career award proposal and also contribute to my recent awards and NVIDIA GPO grant, and as well as STAN early career travel award. So as previously discussed, graphs are one type of nonlinear data structures. They are general language for describing and modeling complex systems and are basically everywhere, such as urban movement, cyber networks, proteins, molecules, and so on. We might have a more intuitive feeling on images where the number and ordering of its neighbors are constant and fixed. Graph actually generalize images by relaxing its constraints on the number and the ordering of its neighbor. So in this work, we further focus on dynamic graphs, which are static graphs adding 10 dimensions. Therefore, their topology represented by age, feature represented by node, change over time. And the generative model needs to capture such type of dynamics. However, existing work typically focus on static graph generation rather than dynamic graphs. Extending existing deep journey models from static to dynamic graph is a challenging task, which requires to handle the factorization of static and dynamic characteristics, as well as the mutual interaction among node and edge patterns. To address these challenges, this work proposes a new novel framework of disentangled dynamic graph model for interpretable dynamic graph generation. Again, I will first discuss notations and the problem formulation. So formally, for different time intervals from 0 to capitalized T, a dynamic graph G consists of G0, G1 all the way to GT is described by its topological and attributed information, where for each time step, we're going to have the lowercase t belong to uppercase key. We have the graph snapshot subscript T represented by both age and node features, where the adjacent matrix is denoted as a binary n by n matrix, and the node features is represented as an n by c vector. So here, n will be the maximum number of nodes, and each node has c features. So for the topology structure, it's kind of discrete, and for the feature, there are continuous values. If there are a connection between nodes I and j, then the element will equal to 1, otherwise it's 0. So in this work, we focus on learning a disentangled distribution based on a set of observed graph snapshot sample from the unknown data distribution. Since we are not aware of the true data distribution, specifically, our model learns the distribution of dynamic graph G generated from latent semantic variable theta, consisting of 4 latent variables F, Z, Z prime, and Z double prime, that are collectively controlled by a time-dependent latent variable F. F here is to observe the time invariant patterns related to the intrinsic nature of the graph that do not change over time. To categorize the time gradient patterns, additional latent variable Z, Z prime, and Z double prime are introduced. Here, Z is to model the dynamics only related to edges. For instance, in dynamic functional connectivity of human brain, the co-activation patterns among different brain regions can change quickly over time. Or Z prime is to model the dynamics merely pertaining to nodes. For example, in traffic network, where the node are load segments and the edges are such as traffic changes, but their connections, edge load network are unchanged. In addition, there are dynamics that simultaneously involve both node and the edges, such as a process of the homophily and influence in social network. So here we leverage the latent arrival Z double prime to account for it. To achieve the above goal, we formulate the proposed generative model as a Bayesian network, as shown here in Figure 8. Where here dashed line denotes the generative model. We also propose two types of inference models shown in B and C. So here B is the approximate inference model of the posterior of the proposed model. So we have conditional independence assumption among latent variable across different time points. And C is the alternative approximate inference model of the proposed model. The difference is it has dependence among time variables and invariant variable. Also, dependency across different time points. We formulate this generative model based on variational autoencoder, which basically maximize the following evidence lower bound of our model. So if you don't really work on variational encoder, it basically provides a probabilistic manner for describing an observation in latent space rather than output a single value to describe each latent state attribute. Now we take the derived observation function to further illustrate our proposed model. Specifically, we have 4 encoders to enforce 4 types of latent representation, and 2 decoders to jointly reconstruct node and edge attributes. In the generation process, edges are generated from both Z double prime, and F, and the nodes are generated from both Z prime, Z double prime, and F. In the inference part, for the factorized encoder, we have a time-independent encoder F to model the conditional distribution of static patterns related latent variable given node and edge attribute. We also have time-dependent encoders Z prime, and Z double prime to model the conditional distribution of dynamic patterns related latent variable here given respective attributes. Also, each time snapshot is decoupled from previous time state without a Markovian chain. For the full encoder, we basically weaken our assumption of conditional independence by assuming time-dependent latent variable Z prime and Z double prime to depend on time-independent variable F. For the experimental evaluation, we evaluate our proposed D2G2 on both real and synthetic benchmark dataset with graph size N ranging from A to 2,500 and a diverse characteristic. Among them, protein dataset captures the dynamics unfolding process of protein peptide, and authentication reflects login behavior from one IP address to another. And the metro dataset shows the mobility network of Washington, D.C. metro system. Additionally, we also consider 3 synthetic datasets, which are scale-free random graph with increasing complexity. We compare our methods with several state-of-art deep graph general models based on a set of metrics to measuring both the similarity between real generative graph in topology and also node features, including net gain, graph RNN, DSPM, graph AE. Among them, graph AE is the only existing method that can achieve graph disentanglement, like to say learning the topology of graph, but also node features, which is also the aim of our approach. The generation are evaluated in terms of both topology and node features simulations. For discrete topology simulation, various maximum mean discrepancy metrics are utilized. So basically, the lower these MND values, the merrier a generative model. For node attributes, which are continuous numerical vectors, its evaluation includes mean square errors, coefficients of determination score, and Pearson correlation coefficients. The result, as one can see, D2G2 based method consistently achieves superior performance on most of matrix across all dataset, although some baseline method perform well on certain specific dataset, they cannot do well for other type of input graphs. So in addition, while methods such as DSPM does not scale well and can only generate smaller graphs, D2G2 enjoys the merit of handling graph with increasing complexity. In terms of node attributes, graph AE is the only method capable of handling node attributes prediction. So the proposed D2G2 outperforms graph AE significantly, while scaling to thousands level graphs where graph AE fails. So in a nutshell, I think the superior performance in both graph topology and the node attribute generation of our model verifies the necessary of its theoretical disentangling design, which captures the underlying graph dynamics very well. Other than the previous short numerical result, which might be kind of tedious, we can also visualize the temporal graph to have an intuitive feeling of the dynamic graph. So here we take one of generated protein graph to illustrate this kind of dynamic graph visualization. In this example, one of the temporal graphs spans all temporal snapshots, where arcs are edges reflecting connectivities among the nodes of the whole temporal snapshot. So the darker the arcs, the closer the connections. Also, node attributes are represented by the color of the node. So you can see the nodes have different colors. When the color is white, which means the method is not capable of learning node features. So in the following, we also use the protein dataset as the running example for the illustration. These slides visualize the graphs generated by D2G2 and the various baselines to quantitatively evaluate the dynamic graph generation capability. So here we can see D2G2 is superior in capturing the underlying characteristic of graphs and is closest to the ground truth in terms of both edges and the node. As you can see, several methods, their nodes are kind of white in color, which means their methods are not capable of generation features by design. We further quantitatively evaluate whether our D2G2 indeed disentangles dynamics and static patterns in node and the edges by randomly sampling one of F, Z, Z prime, and Z double prime, while keeping the other three fixed. So this can control respect factors of the static patterns, edge dynamics, node dynamics, as well as edge node jump dynamics, respectively. Result demonstrates the length representation is indeed factorized and can control the corresponding patterns related to them. For example, as shown in figure A, we fix Z prime and Z double prime while valuing F. So the whole dynamic graph changes evenly.
Because I have a meeting now, and then Andrew's column comes up too. So
Across different time snapshots, which verifies that F indeed controls invariant patterns of the dynamic graph. So differently in figure B, when we instead value Z by fixing Z double prime and F, the topology in different time snapshots for each graph varies, but node attributes stay unchanged. So which verifies that Z indeed effectively control the non-stational pattern in each dynamic graph. So in our paper, we also show that respective patterns can be observed when fixing Z and Z double prime along with other interesting patterns. We also perform two evaluation studies to confirm the necessity of the proposed factorization design. So without time-independent latent representation, the graph generated in figure B captures the underlying node characteristic, but not topology. So this might be allow the latent variables increase by respective dimension of the operative F. The dimension is still too small to fully capture its topology characteristics. On the other hand, with node latent variables, Figure C reveals that the generative topology looks close to ground truth, but not the node characteristic. This illustrates the necessity of separating topology and the node representation. And otherwise, the model might just focus on learning of more complex topology representation and ignore node representation or vice versa. Finally, I will also illustrate and analyze the scalability in the number of nodes of our D2G2 method against comparison method. As shown here, where y-axis is the logarithm base 10 of the runtime in seconds per epoch. As we can see, our methods achieve competitive scalability in general, which is similar to graph RNN and better than graph VAE and PSGM. NetGAN is known for its advantageous scalability, yet lower interpretability. Okay, let's go for this talk. So finally, the overall takeaway to support the practical deployment and deployment of the application that are dynamic in nature. This work discussed to online decision trees with fairness to support social fairness, such as ensuring health equity, and the general framework of deep generative models for interpretable dynamic graph generation, which is quite beneficial for downstream time-consuming data collection domains. Now I will also briefly discuss some other recent projects that I've been working on during my PhD studies to tell a little bit more about my research experience. I might not be able to cover as much details as the previous one, but we'll be happy to discuss more during our later meetings if you are interested. Okay, I start with my PhD with a joint project on human posture recognition in cooperation with NIH in aiding the elderly actively in the independently their life. Then during my research visit at the University of Milano, I also cooperated with the team deploying an intelligent system in aiding self-rehabilitation of the elderly outpatients. More recently, along with collaborators from American University, we completed an extension addressing coherent activity in which different activity happen at the same time can affect each other's recognition, such as when you're walking, you're also moving your head. I have also started collaborating with the team at Montreal Neurology Institute, McGill University, to develop deep learning models to improve the mental health and the quality of patients with psychiatric and neurological illness. Relevantly, we recently completed another work on supervised auto encoder for neural image. Other health relevant projects including automating mammogram analysis to process the mammogram images with Eastern Health. In addition, I also worked on recommender system focusing on medical domain. During my research visit at Paris, I also got the chance to collaborate with Paris Hospital, a PhD Hospital de Paris, on motif discovery in DNA sequence. Most recent, together with other collaborators, we did two works on interpretable visual understanding. So the related health application could be automated clinical decision support, which is similar to Amazon's automated grocery store development. I have also worked on several interdisciplinary projects in other domains, for example, working with geoscientists to address the usability concern of applying this clustering method in satellite cloud type organization. I also spent time on sentiment analysis for cryptocurrency prediction, to name a few. Last, I will discuss future lines of work. So in the future, I will continue working along these things and stay abreast to explore other interesting and meaningful challenges. Specifically, I plan to continue working on AI fairness, considering uncertainty on class label, as well as focusing on devising medical imaging. So NIH has many relevant programs. We submit a head proposal on understanding and addressing health disparity back last month, early this month. National Library of Medicine call for R01 proposal to reduce the gaps and errors in health dataset is also directly related. NSF also has many relevant programs. For example, the FAI programs by NSF and Amazon. So this program has attracted many proposals, but the award map shows Colorado still does not have one. So I think it'd be a good opportunity, especially considering our center's strength in healthcare and also advancing health equity is of great importance to AI fairness. Other NSF and NIH, many other agencies also have directly related programs. So we recently submitted another proposal on addressing racial disparity in cardiovascular disease to the Johnson & Johnson Innovations Decoding Disparity Quickfire Challenge. So in addition, National Institute of Standard and Technologies call for measuring and enhancing the trustworthiness of AI systems is also what I plan to pursue. My postdoc mentor also participated in a national 2-day panel meeting a few months back involving congressmen, machine learning scientists, and physicians focusing on machine learning for healthcare. So apparently, national level attention on healthcare is expected, and many calls for proposal programs are expected to come. For me, I will keep working on this of great importance research to our community. Last but not least, I always open to collaboration. If some of my research work could be of interest to you, I can make a contribution to your research or other joint efforts when possible. Okay, thank you for your attention and happy to take questions.
In Zoom, I have the privilege of being able to clap and applaud. Do people want to hop in with questions? Let's see.
I can ask one. So Wenbin, that was, I apologize if this is a naive question, but is your dynamic graph generation method, is it reversible or generative in that sense? So if I had a set of observed dynamic graphs, could I infer F, Z, Z prime, and Z double prime from that set of graphs, or that evolving graph?
Involvable? I didn't quite understand your question. What do you mean by involvable?
Well, so if I have observations of a dynamic graph, is there a way to infer those 4 parameters? So you
Yes.
give the 4 parameters, I can create these graphs. But suppose I have graphs and I want the parameters.
Parameter will be kind of when you learn the model, the parameter already is part of the model. Right? Is it your question?
Well, right. So what I'm interested in is observing actual dynamic graphs that say were generated from data and trying to infer a model from those observations.
Oh, yeah, this is what we actually want to do. Like for the generation, we don't really want to generate exactly the same graph. That doesn't make sense since we can use the existing one. So for the end of the variation auto encoder, it just is for the variance of data. So ideally for the evaluation, we don't really want exactly the same graphs. That doesn't make sense. So we already have one. We also have new ones, which are kind of, we call it uniqueness. So when you do the measurement, you also want the uniqueness, which means this one are different from the previous already existing graphs. Yeah, that for sure we want to, if this you mean by reverse, we want to get new ones. Otherwise, this method doesn't make sense. If we focus on the previous already exist, it doesn't need to anymore.
Well, but there would be characterizations of those existing ones, right? So if I had one, I could compare 5 different ones that I had and say, oh, the F is different in these, right? That would be the point of doing it, right? Some way of describing these complex graphs that separate out the contributions to the nodes from the topology.
Yes, exactly. I mean, we try to have both uniqueness, but also like the uniqueness based on the existing observation. It should not be random. So we try this on our reason, like I just mentioned, we use VAE. For VAE, just explore the variance based on the existing observation. The variance is not random.
So again, I'm going to echo Larry's comment about naive questions. Let's say that one of the data resources that's kind of interesting to think about is COVID and the N3C data set that it is essentially it's dynamic and it does have nodes and edges that vary over time, and those the relationship between the nodes and edges, if you could characterize those in interpretable terms, could quite quickly help to think about how we would potentially address some population and public health issues, inequities, essentially. So could you use your dynamic graph generation to establish a model over the COVID electronic health record data set and try to define where there are change points in interactions between either individuals and health, whatever the nodes you define are, and the edges, to interpret those in a way that would lead to intervention.
Yeah, I mean, your question almost make me back to my defense dissertation. I think one of my committee members asked exactly the same question you just asked. Okay, so yeah, we try exactly what we're trying to do. So what we're trying to do is, because COVID involves different personnel, so we want to have a privacy preserve. So we call it right now we're working on exactly this extension you just mentioned. We want to have the co-location preserve generation, which means that people can be in the same location, but we want to generate, we're not able to identify the different personnel to preserve the privacy. Yeah, exactly. I think one challenge here is because COVID naturally involve different personnel, we need to have that privacy preserved. That's the main challenge here. We call it co-location preserve generation. This is exactly what we're trying to do at this time.
So I have a question that goes back to the first part of your talk, if we wander back there, which is how these fairness metrics deal with intersectionality, or kind of multiple different axes of discrimination or privilege. Is that something that is readily incorporated, or is that something that where work remains to be done?
And you guys all sound like my committee member. This is also the question asked by my committee member. Yes, you're true. I mean, for the method with fair information gap or that information gap, the limitation here only can focus on one sensitive attribute. We're not able to generate in case we have two sensitive attributes, age and gender or race. Right now, it's limited in this vector. Yeah, exactly. But that's a really interesting way to explore.
And do you think your lab would go in that direction, like from a methodological point of view, or do you think, or are there other questions that need to be tackled first?
Yeah, yes, exactly. The way right now I try to do is for the previous one, for the multiple sensitive attribute, the problem here is I try to sound in naive ways for the fairness scan. I just try to have additional ones here. But it doesn't really help at all, I feel like, when you have multiple. I think I look into the experiment result. The main thing could be also, when we have multiple involved, it's possible just one can dominate all other together. So you only focus on one sensitive attribute. The model ignore other ones. I think that's the problem at this point. And also, I also look into the experiment result. I think kind of the redundancy between the attributes should also be solved. This is really interesting and kind of more practical, I would say. Because in general, like the sensitive attribute will depend on the stakeholder, and the stakeholder will kind of define multiple sensitive attributes instead of just one. This is exactly also what I'm working on at this point, but I don't have clear solution at this point, to be honest.
Gotcha. Let's see. So does anyone else have a question? We're nearing the end of time, so. Okay. Hearing no additional questions, I guess I would like to thank you for coming to visit us today virtually. It was really wonderful to get to hear about your research program and to hear about your thoughts and the challenges in terms of fairness as well as in terms of dealing with dynamic graphs. So thank you so much. I hope you have a wonderful visit and meetings the rest of today and tomorrow, and I look forward to chatting during that time. Thank you.
Thank you for everyone. Thank you for having me. Hope to see you guys later. Bye.